Myself is Divya Bahal, Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that we are going to continue is Mass Transfer Operations 2. So in last lecture we studied about non-ideal solutions, okay? How non-ideality is described. We introduced a new term, that is activity coefficient, which modifies the Rolle's law, and that is applicable for real solutions, okay? So now moving forward, we will study about these different types of non-ideality, okay? How they deviate from Rolle's law, from ideal conditions, okay? The types of non-idealities, let's continue is, now there are two types of non-idealities. Now based on the deviation from the ideality, the solution is classified as non-ideal solution. There are two types of deviations which are from Rolle's law. One is positive deviation from ideality and second is negative deviation from ideality. From name itself you can see the difference is either positive one or negative one. We will study that in detail, okay? So you can see the straight line which shows ideal condition, okay, which follows Rolle's law. The above line which shows positive deviation from Rolle's law, okay? So you can see it is upward, it is concave upwards, whereas the second below line, okay, that shows the negative deviation from Rolle's law. The difference is negative, whereas for above line it is positive. You can see how positive and negative is shown, okay. In last lecture we studied that for non-ideal solution, as we are introducing activity coefficient, so we are naming it as total pressure observed, okay. For real solution the total pressure is your PT observed, whereas for Rolle's law ideal solution it is PT. So the difference between these two, the difference between PT observed and PT, if it is positive then it shows positive deviation, whereas if the difference is negative, okay, if the difference between PT observed, that is for real solution, and that of ideal solution which is PT, if the difference is negative then it will exhibit a negative deviation. Now you can see positive deviation is shown by positive azeotrope, okay. Now here a new term is introduced, okay. In this vapor pressure versus composition graph, you are relating your non-ideal solution and ideal solution, okay. For non-ideal solutions you have two different kind of ways non-ideality exists, okay. One as a positive deviation and second as a negative. We saw that. Now here azeotrope is defined, okay. Positive azeotrope is formed when positive deviation is there, whereas negative azeotrope is formed when negative deviation is there. Now before continuing it, let's have a look on what is azeotrope. So azeotropes are a mixture of at least two different liquids, okay. It can be binary also and more than two components also. Now in this mixture, see the characteristics of azeotrope is their mixture now can either have a higher boiling point than either of the components or they can have lower boiling point, okay. Example, boiling point of my ethanol is 78.4 degrees Celsius and boiling point of my benzene is 80.1 degrees Celsius. Now, azeotrope of benzene and ethanol is formed at 67.68% of benzene. You can see my benzene is the least volatile component, okay. Ethanol is my more volatile component here. So at 67.68%, see here be specific, azeotropes is formed at a specified set of conditions, okay. It doesn't mean that at all weight percent concentration azeotropes will be there. Here it is given that azeotrope is forming at 67.68% of benzene, okay? So you can see here the boiling point of this azeotrope is less than that of ethanol and benzene both, okay. Boiling point of this azeotrope is 68.2 degrees Celsius. It is less than of ethanol, boiling point of ethanol and that of benzene. So you can see similarly it can also be more than that, okay. In next lecture we will study about another kind of azeotrope whose boiling point is more than that of either of its component. So you understood what is azeotrope, okay. From definition you can see the boiling point of this mixture is either more than or less than that of both of the components. For the given example, it is less than both of the components. Now some of the properties of azeotrope, okay. Now azeotropes, okay. Azeotrope occurs when fraction of liquids cannot be altered by distillation, okay. Using distillation you cannot separate the mixtures now. because here liquid and vapor phase composition is same. Okay, we will study that. It means when this mixture is boiled, then vapor has same composition of the components as that is in the unboiled mixture. Okay, try to understand it. As my mixture is boiled, okay, vapors are producing, but those vapors which is produced, okay, the composition, okay, of A and B. Suppose I took the liquid at initial state before boiling, the composition was A is suppose 0.4 and B is my 0.6. Okay, as I am boiling it, so gradually vapors are producing, okay, but that vapors would also be having the same composition. A in vapor phase would also still be 0.4 and B in vapor phase would still be 0.6. So it is also called as boiling without changing. So you can see just phase transition is happening. Okay, liquid is getting converted into vapor, but enrichment is not happening. The same composition is still there in the vapor phase. Whereas for distillation, what was necessary? We studied also that vapor phase composition must be more than liquid phase composition. Okay, in distillation, to apply distillation as a separation process, enrichment must happen. Okay, enrichment, how it occurs is that your component, your more volatile component is getting separated more into vapor phase than that as compared to liquid phase. But in azeotrope, that is not the case. So it is also called as constant boiling mixture. Okay, it constantly boils but enrichment is not happening. So you can say that vapor phase mole fraction is equal to liquid phase mole fractions in azeotrope. If my liquid phase composition of more volatile is suppose 0.6, then in vapor also, when it is vaporizing, still it is 0.6. Again, that is very important to note that your azeotropes, okay, they are formed at specified conditions of temperature, pressure and composition. So now talking about positive deviation from non-ideality, okay, it means the activity coefficient here is more than 1, then and only then it is positive deviation. Let's see how. Okay, now the total pressure of non-ideal solution, which we discussed in last lecture also, it is given as, for non-ideal solution, okay, for non-ideal solution, PT observed is partial pressure of A plus partial pressure of B for the non-ideal system. Okay, so it can be given as gamma A XA PA sat plus gamma B XB PB sat. Okay, gamma A and gamma B, what are those? Those terms are activity coefficient of A and B components. Okay, now for ideal solution, Raoult's law is obeyed, which is given as PT is equal to PA plus PB. The above, okay, PT observed is for non-ideal solution, whereas the second equation, PT is equal to PA plus PB, this is for Raoult's law, ideal solution. So you can see the difference. Now see, gamma is more than 1. Gamma is more than 1, hence a positive factor will take place over here. Okay, it is more than 1 here. Hence your PT observed will be greater 1. Okay. So here, yeah, for Raoult's law I have given XA PA sat plus XB PB sat. But here, as you see in non-ideal solution, gamma A and gamma B is my extra factor. Now because gamma is more than 1, so your PT observed will be more than PT. Now important thing you have to note here is gamma more than 1. It doesn't mean that for only one component it is specified. Okay, gamma more than 1 means this trend is followed by both more volatile and less volatile component. Okay, so hence this is the simple representation of your positive deviation. Okay, from you can see the ideal vapor pressure, that is the trend of Raoult's law. Your actual vapor pressure, it is positively deviated. Okay, it is upward towards the ideal vapor pressure curve. So it means your PT observed is more than PT. Because PT observed is more than PT, hence the difference between PT observed and PT would be positive. Now moving forward, let's understand using an example. Okay, so here I am taking azeotrope of carbon disulfide and acetone. Okay, this is a azeotrope of carbon disulfide and acetone. Now in the left side figure you can see my PB/PA. Okay, how for ideal solution and non-ideal solution a comparison is given. Okay, the straight line is partial pressure of A and B in ideal condition, whereas the upward curve shows you non-ideal but positive. The upward curves of PA and PB, those are for 9 non-ideal solutions. Okay, and similarly For PT, you can see PA plus PB is there. The straight line, again, it is a total pressure which is followed by ideal condition, and the upward curve is for non-ideal solution. Correspondingly, you can see here, okay. In example, now you can see acetone and CS2, okay. Straight line, ideal condition, upward curve for acetone and CS2, you can see it is upward. It means it shows positive deviation. Now, you can see azeotropic condition, okay. The above figure is for vapor pressure one. So at 0.61 only your azeotrope is formed, okay. The above curve, the next curve is pressure versus mole fraction. So you can see the PXY diagram is shown, but at 0.61 curve, my both bubble point curve and dew point curve are merging together. It means at that point there is no difference between vapor phase and liquid phase composition. So my azeotrope condition is forming when my mole fraction of one of the component is 0.61 only, okay. So at 0.61 my azeotrope is formed, and from PXY curve you can see that the difference between bubble point and dew point curve is 0 now, okay. Both the curves, bubble point and dew point curve, are mixing together. Now relating it with pressure and temperature graph. See the above graph, okay, point L, which is showing maximum total pressure. What is that graph? That is pressure versus XY composition. You can see the graph, it is PXY diagram, okay. So that point L is the maximum total pressure which is existing, okay. At which condition, at which composition? At 0.61 mole fraction of acetone, your solution is exhibiting maximum vapor pressure. Now that which was studied in the condition when we studied about boiling point, okay. Maximum vapor pressure means lowest boiling point, okay. Higher the vapor pressure, lower is the boiling point. It means it is boiling very fast. So you can see this positive deviation azeotrope, it exhibits maximum total pressure. So correspondingly you can see, because it is exhibiting maximum vapor pressure, the boiling point would be minimum. So you can see for a maxima condition in PXY diagram, I am having a minima in TXY diagram. Below the pressure and versus XY diagram, there is temperature versus XY diagram, okay, TXY diagram. So you can see that at point L, at L point total pressure was maximum, hence for in TXY diagram you have minimum temperature. This is your minimum boiling azeotrope. So I can say that for a positive deviation is non-ideal condition, okay, when gamma is more than 1, the vapor pressure would be maximum, okay, the vapor pressure of the solution would be maximum and the boiling temperature would be minimum. Hence, it is example of minimum boiling azeotrope, okay. This azeotrope boils at temperature less than that of both the components, okay. So you can see again, which it was discussed earlier also, that your activity coefficient of carbon disulfide and acetone both would be more than 1, okay. Hence, they are showing a positive deviation. Now, as discussed earlier also, the azeotrope will boil at temperature which is less than that of both the components. Now, relating this TXY diagram with the XY curve, okay, with the equilibrium curve. So you can see the boiling point of my carbon disulfide is 46.3 degrees Celsius. Boiling point of acetone is 56 degrees Celsius. Now, as it is minimum boiling azeotrope, okay, the boiling point of azeotrope is now 39.2 degrees Celsius. So you can see the boiling point of this azeotrope is less than that of the individual components, okay. Hence it is called as minimum boiling point azeotrope. So the important note here is this kind of azeotrope, the gamma is more than 1, hence vapor pressure, okay, the pressure is maximum. So as vapor pressure is maximum, the pressure is maximum, hence the corresponding temperature would be minimum, okay. So maxima in PXY diagram, minima in TXY diagram. Now take a look at TXY diagram, okay. At L point, my L point is the condition of azeotrope when y is equal to x. It means at 0.61 mole fraction of carbon disulfide, I am getting my azeotropic condition, y is equal to x. But take a look at TXY diagram. Other than 0.61 composition, concentration, you are getting a difference between x and y. Okay, it means when I am boiling my solution, y and x would be different. It means that. So in the XY diagram, in equilibrium curve, you can see for mole fraction of CS2 less than 0.61, I am getting y more than x. Okay, so I can say that for a mixture, when my mole fraction of carbon disulfide is less than 0.61, for that solution I can use distillation as a separation technique, because for that range, for 0 to 0.61, okay, less than 0.61, as I am supplying heat, okay, as I am supplying the heat, vapors can be enriched. It means my relative volatility is more than 1. But at L point, okay, at 0.61 mole fraction of carbon disulfide, at that condition when my azeotrope is formed, my relative volatility is 1. It means at 0.61 mole fraction of my carbon disulfide and the remaining of acetone, now both carbon disulfide and acetone are equally volatile. Hence, now when I am supplying the heat, the vapors that would be produced would be having the same mole fraction as it was in the liquid phase also. Now, next is after, okay, when more than 0.61 mole fraction is there, it means x is more than y. Here if I am using distillation, it is the no meaning, okay, because vapor enrichment is not happening. So it means to say that the mole fraction of carbon disulfide would be more in liquid only. With heating, with application of heat, vapors, it is not enriching in the vapor phase. So it is useless to use distillation as a separation process. Now here I have to use another separation method. See, separation can occur. Your carbon disulfide is separating in a liquid phase, but it is not advisable to use distillation here, because in distillation the prime object is to enrich your more volatile component in vapor phase. So the third is y is equal to x. So you can see at L point alpha equal to 1, it means my relative volatility is 1. Again it means both the components carbon disulfide and acetone are equally volatile in nature. And now once this azeotropic condition has reached, that is once 0.61 mole percent has been achieved, okay. Now once my solution has reached this level where carbon disulfide is 61 mole percent and the rest in acetone, now when I am heating this solution, the vapor would also be produced having the same mole fraction. The vapors now will have 61 mole percent of carbon disulfide and the rest is acetone. So you can see at this point, at L point, okay, even when I am supplying the heat, no enrichment will occur, okay. Enrichment will take place until my mole fraction of carbon disulfide is less than 61%, okay.